I am Sheikh Mahbub Basha. Welcome to my channel. Happy learning. Welcome students. Welcome to the new chapter, that is Human Eye and Colorful World. Let us start the first topic. We'll start with the structure of human eye. The eyeball is nearly spherical in shape. The front portion is more sharply curved. This front portion is a transparent protective membrane. It is called cornea. Cornea is the portion which is visible from outside. Behind the cornea, there is a place filled with a liquid called aqueous humor, and behind this aqueous humor we have a muscular diaphragm called iris. Iris is the colored part that we see in an eye. Iris has a small hole in it which is called as pupil. The pupil appears black because any light falling on it goes into the eye, and there is almost no chance of light coming back to outside. Iris helps in controlling the amount of light entering the eye through pupil. In low light condition, the iris makes the pupil to expand so that more light is allowed to go into the eye. In bright light condition, the excess light that entering into the eye is controlled by the iris. The pupil contracts and thereby prevents the excess light not to go into eye. Thus, iris enables pupil to act as a variable aperture for entry of light into the eye. Behind this iris, there is a crystalline lens which is responsible for the image formation. The lens is hard in the middle and gradually becomes soft towards the outer edges. The light that enters the eye forms an image on the retina. Retina is the sensitive membrane that receives the light and sends the signal to the brain through optic nerve. The distance between the lens and retina is about 2.5 cm and it is fixed. The lens is surrounded by ciliary muscles which helps the eye lens to change its focal length by changing the radii of curvature of the eye lens. When the eye is focused to a distant object, the ciliary muscles are relaxed so that the focal length of the eye lens has its maximum value. When the eye is focused to a closer object, the ciliary muscles are strained and focal length of the eye lens decreased. The ciliary muscles adjust the focal length in such a way that the image is formed on the retina and we see the object clearly. This process of adjusting focal length is called accommodation. The eye lens forms a real and inverted image of an object on the retina. The retina is a delicate membrane which contains about 125 million receptors called rods and cones, which receives the light signal. These signals are transmitted to the brain through optic nerve. The brain interprets these signals and finally processes the information so that we perceive the object in terms of its shape, size and color. Let us move to the next topic. Next topic is angle of vision. A person when tries to look at the nature, he is able to see only a part
he cannot see everything that is present there, and it is based on the ability of the eye. He can see only a part of things that are in front of his eyes. Notice the area that he is able to see and draw the boundary lines from his eyes. Then draw a line normal to the eye. You will find that the angles are 60 degree and 60 degree. That means this person is able to see the things in front of his eyes that are covered by a cone having angle 60 degree with its axis. So this angle 60 degree is called the angle of vision. Okay, right.
What is actually mean by a healthy eye? First of all, let us quickly understand few important parts of human eye and their functioning. This is eyeball, its eye lens, its retina, let it be optic nerve, it is connected to brain. There is an object. The rays coming from the object are converged onto retina, and whatever the retina received is sent to the brain. Our brain reads what the retina receives. If a clear image is formed on the retina, then the vision will be clear. Case 1. Take an object at a distance 25 centimeter. The rays coming from the object are converged to retina by this eye lens. It is recognized by the brain, so it says that the image is clear. Case 2. Take the same object now at 50 centimeter distance. Again, the rays are converged onto retina and the brain identifies a clear image. Case 3. This time, move the object away, let it be 100 centimeter. Again, the rays are converged onto retina and the object is seen clearly. Image is clear. Case 4. This time, let the object is at a 5 meter distance. Again, a clear image is formed. Case 5. The object is moved to long distances, for example 50 meter. The image is clear. Now the object is taken at infinity, and in this case also the image is clear. Case 7. Now take the object very close to the eye. As shown here, it is less than 25 centimeters. This time, observe carefully. The rays are converged behind the retina and the clear image is formed somewhere else than retina. So, the image formed on the retina is not clear, and the same is identify the brain. That means in this case the object is not seen clearly. The image is blurred. If a clear image is formed on the retina for any distance of the object from 25 centimeter to infinity, then the eye is said to be healthy. Here, actually, the eye lens adjusts its focal length by adjusting its curvatures. It makes use of ciliary muscles for this purpose, and this is called as accommodation. What is near point? What is far point? What is least distance of distinct vision? To understand near point, far point, and least distance of distinct vision, let us start an activity. Note down the observations carefully. So let it be your eye. Place an object at some distance. If you can clearly see this object, put a tick mark, or you can put a green button. Then slowly move this object towards your eye. Each time, if you can clearly see this object, put a green button. Continue this process. Move the object towards your eye. If you can clearly see this object, put a green button. Continue this process. Observe carefully. Now this object is blurred. It is not clearly visible, so put a red mark. On further moving the object towards your eye, again it is blurred, so put a red mark. Now do the same experiment on the other hand. Increase the distance of the object from your eye, move the object away from your eye, and each time note down whether the object is clearly visible to you or not. If it is clearly visible, put a green button. If it is blurred, then put a red button. Here, as the object is moved away from the eye, still it is visible, so green buttons continues. Still the object is visible. Now the object is blurred. That means the eye is not able to see this object clearly, so put a red button. Again, on further moving the object away, put a red button. So this is the visible region, green shaded. This red shaded area is the blurred vision area. One is close to the eye, one is far away from the eye. For this visible region, you have two boundaries. Closest to the eye is the near point N. Here, the distance from the eye to the near point is called least distance of distinct vision. And farthest to the eye is the far point F. Conclusion. The nearest but clearly visible point is the near point. The farthest but clearly visible point is the far point. The distance to the near point from the eye is the least distance of distinct vision. What is myopia? How it is corrected? Let us quickly recollect the basics related to healthy eye. This is a healthy eye. It is able to see various objects lying at various distances, the stars at a distance infinity, the mountains at few kilometers, a vehicle passing by which may be at few hundred meters, a tree which may be at few tens of meters, the blackboard which is at few meters, persons sitting at 1 or 2 meters, a book in his hand which is exactly at 25 centimeters. These two objects which are at a distance less than 25 centimeters blurred. This region from the eye up to a distance 25 centimeter I am calling as blurred vision region. So it is common to every human eye. This point N is the near point. That means the closest and clearly visible point. So it is at 25 centimeter from the eye. This green shaded region is the clearly visible region for this healthy eye. This point F is the far point. That means the maximum distance and clearly visible. So this F is called a far point. If an eye is able to see clearly and distinctly all the objects that are placed at a distance of 25 centimeter and above, then it is said to be a healthy eye. Now let us understand myopia. This is a myopic eye. This eye is unable to see the objects that are at long distances. So this eye is unable to see the objects in this red shaded area clearly. This eye is able to see only this region from the near point N up to few meters. That region is shaded green. The far point for this eye is not at infinity, but it is at few meters or tens of meters from the eye. Here the eye is able to see clearly and distinctly only the objects placed at a distance 25 centimeter and up to few meters from the eye. This defect is called myopia. What can we do to correct myopia? We need to select a biconcave lens to correct myopia. When a biconcave lens is introduced as spectacles to this myopic eye, observe the changes. The far point is shifted away from the eye towards infinity. So the visible region range is increased. A concave lens is introduced as spectacles, then the far point is shifted away from the eye. Clear vision range is increased. Thus, myopia is corrected. Questions. First of all, let us quickly recollect the basics related to healthy eye. Let us quickly understand few important parts of human eye and also their functioning. This is an eyeball. Let it be its eye lens. This is retina. This one is optic nerve connected to brain. There is an object in front of the eye. The rays coming from the object are converged to retina. The signal is sent to brain and brain reads the image formed on the retina. Our brain reads what the retina receives. If a clear image is formed on the retina, then the vision will be clear. Now let us understand myopia. Example 1. Here is an object. The rays pass through the eye lens and are converged to a point before retina, and the image is blurred. Example 2. Here is an object. The rays are converged to a point before retina and the image read by the brain is blurred. The inability of an eye to get a clear image on its retina when the objects are placed at long distances but is able to get a clear image on its retina when the objects are placed at shorter distances is called myopia. It is due to loss of efficiency of ciliary muscles to adjust the focal length of the eye lens. What can we do to correct myopia? As the problem is overconvergence of the eye lens, we need to decrease its converging nature, or we need to increase the divergence. We need to select a biconcave lens to correct myopia. Let us understand with few ray diagrams. Selecting a defective eye, myopia problematic eye. A concave lens is introduced in front of the eye. The rays coming from the object are first diverged by the concave lens and then converged by the eye lens, and the image is formed on the retina. Hence, brain reads a clear image. Let us go for another example. This is a defective eye having myopia problem. A concave lens is introduced in front of the eye. The rays are first diverged by the concave lens and then converged by the eye lens, clear image on the retina, and the brain reads clear image. Once more, defective eye, an object, rays are converged to a point before the retina and the image read by the brain is blurred. Whereas the defective eye with a spectacles concave lens, there is an object, the rays are first diverged and then converged to give clear image on the retina, the brain reads a clear image. Similarly, another example, there is an object, the rays are converged to a point before the retina and the image read by the brain is blurred. Whereas when spectacles concave lens is added, the rays are first diverged and then converged to give a clear image on the retina, hence the image read by the brain is clear. Conclusion. Any eye with defect called myopia, when aimed to see objects at longer distances, the rays are converged before the retina and the image on retina is blurred, hence the vision is blurred. When a biconcave lens is used as spectacles, then the problem is solved and the vision is clear. What is hypermetropia? How it is corrected? Now let us understand hypermetropia. This region starting from 25 centimeters is shaded red and this region is not clearly visible to this hypermetropic eye, and thereafterwards this green shaded area is clearly visible area to this eye. Therefore the near point is not at 25 centimeter but it is slightly greater than 25 centimeters. However, the far point is still at infinity. What can we do to correct hypermetropia? We need to select a biconvex lens to correct hypermetropia. Here, a biconvex lens is introduced in front of the eye in the form of a spectacle, then the near point is shifted towards the eye. A convex lens is introduced as spectacles, then the near point is shifted towards the eye, clear vision range is increased, hypermetropia is corrected. Now, let us understand hypermetropia. Example 1. There is an object in front of the eye. The rays are converged by the eye lens, but they are meeting at a point behind the retina. So, the image is blurred. Example 2. There is an object in front of the eye. The rays are coming from the object are converged to a point behind the retina. So, the image read by the brain is blurred. The inability of an eye to get a clear image on its retina when the objects are placed at shorter distances, but is able to get clear image on its retina when the objects are placed at longer distances is called hypermetropia. It is due to loss of efficiency of ciliary muscles to adjust the focal length of the eye lens. What can we do to correct hypermetropia? As the problem is lesser convergence of eye lens, we need to increase the convergence. We need to select a biconvex lens to correct hypermetropia. Let us understand with a few ray diagrams. This is a defective eye having problem called hypermetropia. Let it be example 1. There is a convex lens placed in front of the eye. The rays coming from the object are first converged by the external convex lens and then again converged by the eye lens. So the rays meet at a retina. A clear image is formed on the retina and the image read by the brain is clear. This is also a defective eye. Let it be example 2. A convex lens is placed in front of the eye. The rays coming from the object are first converged by the external convex lens. Then the rays are again converged by the eye lens. The rays meet on the retina, so a clear image is formed on the retina and a clear image is read by the brain. Once again, defective eye having the problem hypermetropia. The rays are converged by the eye lens to a point behind the retina, so the image read by the brain is blurred. On the other hand, if a convex lens is used as spectacles, the rays coming from the object are converged by the spectacle lens and then by the eye lens, so that they meet on the retina. A clear image is read by the brain. Another example, defective eye hypermetropia is the problem. The rays coming from the object are converged by the eye lens but to a point lying behind the retina. Therefore, the image read by the brain is blurred. On the other hand, if a convex lens is introduced as spectacles in front of the eye, the rays coming from the object are converged by the external lens and then again converged by the eye lens, and they meet on the retina and a clear image is observed by the brain. Conclusion. An eye with a defect called hypermetropia, when aimed to see objects at shorter distances, the rays are converged behind the retina and the image on the retina is blurred, hence the vision will be blurred. When a biconvex lens is used as spectacles, then the problem is solved and the vision is clear. What is presbyopia? How it is corrected? Let us understand presbyopia. This is a defective eye. It has a problem called presbyopia. This eye is unable to see this red shaded area, that is from 25 centimeters up to few centimeters, as the clearly visible and nearest point is near point. For this eye, it is not at 25 centimeters, but it is slightly beyond 25 centimeters from the eye. And this presbyopic eye is also unable to see the objects lying at long distances. The red shaded area is not clearly visible to this eye, so the maximum distance and clearly visible point is F, called as far point. It is at a distance less than infinity. Then this green shaded area is the area visible to the eye. Here, the eye is not able to see clearly and distinctly the objects placed at shorter distances and also at longer distances, but is able to see the objects at intermediate distances. The visible region is shorter. The defect is called presbyopia. What can we do to correct presbyopia? We need to select the combination of a biconvex lens and a biconcave lens to correct presbyopia. When a suitable biconvex lens is introduced as spectacles, the near point is shifted towards the eye to a point 25 centimeter from the eye. If a biconcave lens is introduced, then the far point is shifted to infinity. Then the visible region is increased. A convex lens plus a concave lens is introduced as spectacles, then the near point is shifted towards the eye and far point is shifted towards infinity. Clear vision range is increased. Presbyopia is corrected. Now let us understand presbyopia. Let us examine few ray diagrams. Example 1. This is an eye and there is an object. The rays coming from the object passing through the eye lens are converged to a point before retina and the picture read by the brain is blurred. The eye is unable to get a clear image on its retina when the objects are placed at longer distances. Example 2. This is an eye and there is an object nearer to the eye. Rays coming from the object are passing through the eye lens and they are converged to a point behind the retina and the image read by the brain is blurred. The eye is unable to get a clear image on its retina when the objects are placed at shorter distances. The inability of an eye to get a clear image on its retina when the objects are placed at longer distances and also when the objects are placed at shorter distances but is able to get clear image on its retina when the objects are placed at intermediate distances is called presbyopia. It is due to loss of efficiency of ciliary muscles to adjust the focal length of the eye lens. What can we do to correct presbyopia? Let us understand with few ray diagrams. Example 1. This is an eye and there is an object at longer distances. The rays coming from the object are converged to a point before retina and the image is blurred. If a concave lens is introduced as spectacles in front of the eye, then the rays passing through the concave lens are first diverged and then converged by this eye lens, and hence rays are meeting exactly on the retina, giving a clear image on the retina which is read by the brain. Example 2. Here is an object at a shorter distance. The rays coming from the eye after passing through the eye lens are converged to a point behind the retina and the image read by the brain is blurred. Whereas if a convex lens is introduced in front of the eye as spectacles, then the rays coming from the object are first converged by the external lens and then again converged by the eye lens, and finally clear image is formed on the retina and the image read by the brain is clear. So we need to use a concave lens and also a convex lens to correct presbyopia. Let us make a mixed lens using concave and convex lenses. Making a mixed lens. This is a biconcave lens and this one is a biconvex lens. Cut it into halves. Take half from concave and half from convex and fix these two pieces as shown here. Half concave plus half convex gives a mixed lens. When a mixed lens is introduced as spectacles in front of the eye, the rays coming from the object at longer distances are passed through the concave part of the mixed lens and they are finally converged to retina, giving a clear image on the retina. Whereas the rays coming from an object at shorter distances are passed through the convex part of this mixed lens and they are converged to retina. A clear image is formed on the retina and the clear image is read by the brain. Thus, presbyopia is corrected.